Hi, in this video, we're going to talk about multiple linear regression models, specifically how partialing out effect works. Right now, in the previous video, we discussed a simple linear regression model, but of course, as we have already established, simple linear regression models may not work and it may be confounded in the sense that it violates one of the crucial assumptions of Gauss-Markov, which is the zero conditional mean assumption, or that the error term must not be correlated with your regressor. Now, our model in the previous video is wage on experience. Now, that model, that simple linear regression, will work if we can safely assume that experience is not correlated with any other factors that are not captured by the model. But unfortunately, we cannot safely assume that. We know that in real life, experience may have a bearing on some other factors that can affect wage. Like, for instance, a person's education, a person's the person's upbringing, right? The parent's education, the father's education, the household that they lived in, their previous income, and so many other factors that you can think of, right? Now, to resolve that, we can add more variables. We can add more variables in the model that can effectively filter out those confounding effects, right? And that will enable us to get a better estimate of the coefficient of experience, in this case, B sub 1, or in textbooks, you call it beta 1, right? While filtering out all of those confounding effects that experience may capture, right? Now, in Stata, it's pretty straightforward. So before we proceed, let's examine, or let's revise the model, right? So we still have log of wage. Let's try to revise the model by including some other factors. But before that, let's try to load the data set first and have it here, right? So we have wage, we have edu, experience, tenure, right? Female, marital status, you have marital status dummies, and so on, right? So let's improve, in a sense, this model by including some other factors that you may think are correlated with experience, right? Now, at this stage, you may think, oh, this is very easy, right? You just had to add as many variables as you want if you wanted to rule out all of the other factors that could be correlated with experience. Now, this is where the economics part of econometrics comes in, right? Theory must inform the specification of your empirical model, right? You shouldn't just add any variables as you wish in an empirical model, in a regression model. So it's not like a shotgun, right? It's not like a shotgun where you just shoot uh, um, haphazardly. And you just shoot your gun everywhere else, right? With some unfortunate collateral damage. Of course, that's not the case. When you construct your empirical model, it should still be informed. I should still be informed by theory, right? Uh, the specification and the variables that you'll have to include in your empirical model should be based on the conceptual framework that you have established. And of course, this conceptual framework is based on the literature, right? It's based largely on the literature. What does the literature say about this particular relationship? What factors should we include? And that is based on that should be based on theory, right? At this stage, let's use our intuition and let's just say that experience may be correlated with the person's educational attainment. So we add another parameter, we add another variable, and that's edu, right? And let's factor in, of course, we will still discuss more about dummy variables later on, but let's try to factor in one categorical variable to capture wage differentials between males and females. And let me add this dummy variable female just to make the model more realistic. So this is how your multiple linear regression looks like. Now, there is, of course, this is done in one go. This is estimated in one regression command, but at the back of it, you have an entire process of partialing out going on, right? So once you include education and female in your regression model, you're effectively partialing out the correlation of experience with education and female, right? You're removing, when you include them in the model, you're explicitly filtering out the correlation of educ on experience and the correlation of female on experience, all right? So you're just left with the pure, you're sort of left with the pure experience effect on the person's log of wage. And how do we estimate this? Of course, very simple. Just type regress. In Stata, it's very simple. You just type regress L wage, right? Experience educ. And since this is a dummy variable, we'll use the factor function. And this gives us the regression results. Pretty nice fit. You have, well, don't look at the, of course, you don't necessarily look at the R squared, but in terms of significance, it's practically significant, all right? So previously, we established that the effect of experience on wage is around 0.4, but now that we have filtered out education in female from experience, we now have a better, we now have a larger estimate for experience, and it's now at 0.9%, right? 0.9%, approximately 0.9% increase in log of wage for every year of experience, right? So this is where the term ceteris paribus comes in. Holding education and female constant, assuming everyone else has the same education, everyone else has the same, belongs to the same gender group, right? Wages increase by 0.9% for each additional year of work experience. You're basically controlling for education and female. When you include them in the model, this is where the term controlling for comes in. When you include them in the regression model, you're practically controlling for those confounding factors. Something that you cannot do if you're just running a simple linear regression model, or if you just have one dependent, one independent variable, right? So that is where controlling for comes in. When you add them in the model, you're explicitly holding them constant. Right? You're holding them constant. You can check the slides for how the maths behind that, but it's a little bit of calculus, right? When you explicitly include them in the model, it allows you to run that kind of calculus, right? You can hold all of those other factors constant and look at how wage behaves with respect to experience. Now, let me just describe how that partialing out works, right? So behind this single command, there's an entire lot of partialing out going on. In effect, we're trying to remove, before running the regression, you're trying to remove the effect of education and female on experience. So let me demonstrate that when you do that partialing out manually, right, you will get the same result. So look at the results carefully. You have 0.0094, right? So let me run the partialing out. Let me show you how the partialing out effect works. So when you partial out education and female from experience, you wanted to remove the portion, the variation within experience. Do you want to remove the education and female part from experience, right? And you wanted to just have the entire, you want to be left with the actual experience, or actual variation of experience itself. So to do that, let's try to regress. So let's type it as part 1. Part 1, filter out educ and female from experience. You're filtering out that correlation between education and female. That could affect, of course, the coefficient estimates for experience. So let's regress experience on education and female. All right. Now, when you run a linear regression or when you specify a linear model like this, you're sort of decomposing the dependent variable into two parts, the deterministic part and the random part, right? So here in part one, we're trying to remove this effect. We're trying to remove the education and female effect on experience. And we just wanted to be left with the pure experience effect. So to do so, we'll need to run the regression and obtain the residuals, right? So to obtain the residuals, we'll type predict, say experience hat. Let's type experience hat and type the option resid. This gives you the residuals, which is practically the part of experience that is not affected or practically is not correlated with edu and female. Okay. Now part two, we use the residuals x per hat in regressing log of wage. Right. Now once we get this, we run the regression, regress L wage on x per hat. Right, so let's run this. All right, so what do you notice? Right, you have an identical, exactly the same coefficient estimate for experience hat and the coefficient estimate for experience in the multiple linear regression model. In other words, when you do this multiple linear regression model, you are factoring out the correlation of edu and female on experience, right, to get the actual effect of experience on log of wage. And you can also do this. You can also do this for the other regressors, right? You can also do this for the other regressors, and you will get the same. You'll practically get the same results. Okay? So that's how the partialing out effect. That's how the partialing out effect works. Right? We filter out the part where X, in this case experience, is correlated with the other regressors, right? And then when we run the regression, we're basically getting the effect of experience without these confounding factors. Of course, you don't need to do this two-step process. You don't need to do this two-step process. You just have to include them in your regression model. Okay. Now, of course, we can do the same. We can do the same in R. Try to do the same in R. Okay. So let's have a more complete model. Let's type M2, right? And same formula, same function. So you have L wage, but this time we'll include educ and an indicator function. This is important. Okay. Or factor, sorry. Sorry, it's not I. It's supposed to be factor. Right. Factor. Specifying it as a dummy variable. Factor. Right. And summary. And we get, of course, we get the same results. So you have 9%. Yeah, the 9% is in the strongly significant, more significant than our earlier results. Right. Now, about the partialing out, well, we can do the same. So let's run the regression on experience. Right. Let's run the regression on experience. Okay. Or maybe you can do it straight here. So you have x per hat. Resid is the function that allows you to obtain, or that gives you the residual of the linear regression model. So here we're trying to regress experience on educ plus female. Okay. See if it's gonna run. Oh yeah, it runs, right? So we now have shortcut. We now have our experience hat. Now if you try to run the regression, let's not save it anymore. Let's just type summary lm L wage on hat, and you get of course, you get the same, you'll get the same result. So it's factoring out, right? You're factoring out the effect of educ and female on experience, right? In order to have a precise measure, of the effect of experience on log of wage. Okay. Now, in the second part of the video, let's try to do a simple simulation to show you the consequences of omitting a relevant variable in a model and adding irrelevant variables in a model. Now, omitting variables may be something that one is too careful of, right? Because in most practical applications, some people tend to add so many control variables in their model, all right? So of course, there could be an issue of availability of data, which of course forces you to omit a certain variable. But these are two problems that are typical in regression analysis, right? You either omit an important or relevant variable in the model, or you add too many variables that are otherwise irrelevant in the model. And this is magnified if the correlation among these independent variables are too high, right? If there is multicollinearity, right? Multicollinearity is becomes relevant becomes a potential problem if those additional regressors, if those added regressors uh, are not relevant to your dependent variable. Now, to examine how omission of relevant variables or inclusion of irrelevant variable works, let me do a simple Monte Carlo simulation using Stata. In the last part of the video, we're going to show it. I'm going to show it how to do such simulation using R. Okay. So let's try to set up the model first. Right? Let's try to set up the model. So suppose we have a simple y is equal to say 10 plus 0.20, let's say 20 plus 1.9 times x1 plus 0.5 or 0.5 times x2. Suppose this is your true model, right? Suppose that's your true regression model. Okay, so let's try to set up the data. And what we're establishing here is, what if we drop x2, assuming that x1 and x2 are correlated, and assuming that of course x2 is relevant to the model y, relevant to y, okay? Given this parameter, so obviously it's relevant to y, right? So let me set up the simulation first. So let's clear everything. Let's set the seed. Okay. set C. Let's set it at, say, what, random number 2, 3, 6, 7, 8, 9. Okay. Now, before anything else, before we come up with the data, let's set up our correlation matrix first. So let's define matrix A as 1, 1, and let's say there is a correlation, positive correlation of, say, 0.6, and you have 0.5, 6. Okay, so you can just like that. So you have this matrix. So this correlation matrix it basically establishes the relationship between x1 and x2. Okay, so let's run this. Simulations. Okay, just to make sure that the matrix is correct, let's try to display matrix list. All right, so C1 and R1 refers to X1, C2 and R2 refers to X2. And we're saying that X1 and X2 are correlated by 0.6, right? So let's create random variables. So let's set draw norm, right? Draw norm X1, X2 with a correlation matrix of A. Sorry, let's set the observations. First set obs, say you have 1,000 observations. Okay, and let's draw norm. So we have drawn random values. Basically, we have drawn random values for x1 and x2, right, from the normal distribution, and assuming that there is a correlation of 0.6, or using the correlation matrix A. And we're assuming that x1 and x2 are correlated by 0.6. Okay, so now that we have the data for x1 and x2, let's get the data for y, right? So let's set this as y true equals 20. So basically, this is the data generating process, right? So you have y true 20 plus 1.9 times x1 plus 0.5 times x2. Okay. Sorry, x2. So now you have your data. You now have your data set. You now have your data set. Okay. Now, to run the simulation, so our case here is that this is the true data generating process. You have 20 plus 1.9 times x1 plus 0.5 times x2. Now, we wanted to observe what happens, right? We wanted to observe what happens if, number one, we run this regression 1,000 times over through Monte Carlo simulations. And number two, what happens if I try to omit x2? What happens if I try to omit x2 given that x1 and x2 are correlated? What happens to the distribution of the estimates, right? The estimates for beta 1, right? If I remove x2, will it still be around 1.9, or will it be a little off, or will it be way off than 1.9? So that's the goal of this exercise, right? So let's try to save this data set for the meantime. Right? Save y true. So we're gonna use this. We're gonna use this later. Okay. Now, let's try to program, let's start programming the function that will run the simulation. So generate the program that will run the simulation, or more like the model, or set up the model that will run the simulation. So let's name that program uh, program define, let's say M1. And let's set the args at C. Now, this program, so let's type the capturing end of that program. So basically this program will run. After I define this program, I will run simulate, which will execute this program 1,000 times over and then generate certain results. Okay, so under this program, I want Stata to load the data. So use y true clear, and then I want to randomize y, right? So other than the data generating process, which is this one, so you have to generate y equals y true plus some random error term, right? So basically this R norm will be your error term. Okay, that's your epsilon. R norm, or let me just make sure that should be R normal. Yeah, it should be R normal. And then we'll do the regression. So y on, we'll regress y on x1, x2. Right? So that's M1. Okay. Now, after defining this program, we will then run the simulations. Right? By typing simulate, let's just look at the coefficient estimate. Let's look at the coefficient estimates. Okay. Simulate the coefficient. Okay, and identify the number of reps. So let's say that we wanted to run this program 2,000 times over, and let's call for that program. What's that program? It's M1. Okay, so let's run this again, and it's now running the simulations. So basically, we're regressing y using different sets of samples, right? Monte Carlo simulations. We're doing 2,000 repetitions with different set of samples, right? At least for the error term, right? And then we now have the coefficient estimates. So basically, these are 2,000. These are 2,000 version or 2,000 estimates for beta x1 and beta x2, and for the constant. So maybe you can take a look. Let's try to take a look at the distribution of the coefficient estimates. So we can do that by typing sum, right? Right. So if you notice, the average of all of those estimates is pretty close to our parameter, or our population parameter of 1.9. So this means that OLS is unbiased, in a sense that when you take the average, when you do that regression over and over again, you take the average of those estimates, you will hit the true population value, you hit the true parameter value for the data they're generating process of y, which is at 1.9. You also get 0.5 for x2, and you also get a really nice estimate, or you get a really nice estimate for the intercept, which is at 20. Which means that at this stage, at this base level, the model is correctly specified, and OLS is not OLS is a good estimator. It won't pose any problems. Okay. And we can also show some kernel density function. So let's type two-way k density. Let's just look at x1. And you see it's distributed, it's averaging, where it's distributed, it's clustered towards uh, 1.9, which is the true population parameter value, right, for the data generating process of Y. Okay. Now, this is the base model. Now, omit, what if we omit x2, right? While retaining the same data generating process. This is still your true population. This is still your true population model, right? This is still your true population model, but say because of carelessness, you are not able to include x2. We know, you know that at the population level, y is determined by both x1 and x2. But suppose at the empirical level, you weren't able to include x2, right? So let's try to run this. To do so, we'll retain this data generating process, but in the program, we'll omit x2. Okay. So let's run this. So let's drop the program. Or maybe let's just define a new program. Let's just define a new program. Let's name it M2. But this time we'll remove variable 2. And let's run the simulations for M2. Let's run the simulations for M2. Okay. Okay, let's define this program. Let's run the regressions. So it's running the regression 2,000 times. Now let's look at the summary stats. Let's look at the distribution of x1. So what happens? The intercept is not really problematic. It's still close to your population value of 20. But look at the coefficient of x1. From its true value of 1.9, it's now way off, right? It's now way off. It's now at 2.19, right? It's now at 2.19, right? It's way off the population. It's way off the population value of 1.9, right? So it basically increased from 1.9 to around 2.19, right? So in other words, if you omit a relevant variable, in your regression model, if you know that at the population level, x2 is relevant, but you did not include it in your OLS regression, then OLS will yield biased estimates, right? No exceptions. It will yield biased estimates for all of the remaining variables in your model. In this case, x1. In this case, x1 becomes confounded. Right? X1 becomes confounded. The resulting estimate is way off its population value of 1.9. Right? So that's what happens when you omit a relevant variable in the model. Now, of course, that's not the usual problem because you always have your theory, you always have your intuition, right, to tell you whether you have included a relevant, whether you have excluded a relevant variable or not, or if OLS yields biased estimates, right? So you have your economic tools to tell you, and you have your economic concepts to tell you whether whether your estimation results make sense or not. Okay. Now, what if this time we include irrelevant variables in the model? Okay. Now we will have to tweak some things. I will now have to tweak some things. Okay. So let's copy this. Right? Still base 1. Let me just drop the program here. Program drop M1. We'll use that later on. Let's tweak this a bit. Right? Let's tweak this for a bit. And let's instead of allowing for a correlation, right? Let's say that tweak things a bit, right? So we'll still retain this correlation between X1 and X2. Let's say they're strongly correlated like that, but let's try to modify the data generating process for Y such that X2 becomes irrelevant. Right? It means that Y is only determined by some intercept, by some constant which is equal to 20, and you have X1 as your relevant variable. So X2 doesn't really matter. But what if, because of carelessness, right, you decided that even if the intuition is far off, you decided to include X2 just to be safe, quote unquote. Right. So what's going to be the problem? What's going to be the trade-off? Well, conceptually, what will happen is that it will increase the noise in your model, right? Your model may still be unbiased, but it will increase the noise, right? It will increase the noise of your model. It will increase the standard errors of OLS, right? Or if your OLS estimator, right? Which will of course yield in a less likelihood of less likely that you're gonna obtain statistical significance if that's the case. Okay, so let's try to run this. Let's program drop, and we'll try to run the simulation. This time, let's include the standard errors with 2000 repetitions, and let's run M1. Oh, by the way, before we run that, you may want to look at the standard. So we don't have the standard errors yet, but let's try to run this again, and let's try to run the first model, right? And look at the standard errors. Sorry, program drop M1. Let's include the standard errors in the results. Okay. Let's drop all programs. Okay. Let's run this. All right, so let's look at the summary and try to observe the standard error of X1. Right, so the average standard deviation, the average standard error for X1 is at 0.0008913, pretty small, right? Pretty small. And at the base model is practically correct, right? Now, what if we change, right? What if we change the base model, right? What if we change the base model and now we included, or sorry, maybe this is better if we remove X2 already. Right. Sorry, let me correct that. So let's run the correct model instead. So instead of using the first one, so we drop this. Okay, this is more comparable. So you have your simulations running, 2000 regressions, right? That will yield 2000 coefficient estimates and 2000 standard errors. So let's try to sum it up. Sum. So take note of the standard error. The average standard error is at 0.03, right? So 0.03. 319, right? For the correct model. So this is your correct base model, right? Now, what if we include the irrelevant variable x2, right? And you know that x2 is correlated by this much. So let's try to jack it up a bit. Let's make the correlation between x1 and x2 at 0.8, right? And what if I now include x2, an irrelevant variable in the regression model? What's going to happen to these? What's going to happen to this standard error of x1? So let's run this. And just look at the standard error of x1. So from 0.03, you're now jacked up to 0.054. All right. X2 is irrelevant. It's actually close to zero, but yet you still included it in the model, thereby adding noise to your regression, in a sense that the standard errors of x1 and x, the average standard errors for all of these 2,000 iterations, basically increase the standard errors from 0.03 to 0.05. So in conclusion, adding irrelevant variables in your model doesn't really help, because it increases the standard errors of your OLS, right? OLS estimator. It increases standard errors of your estimates. Okay. And you're less likely, if your standard errors are high, you're less likely to obtain statistical significance. Okay. Now, of course, this is just a simulation. So this is a controlled data set. But in actual practice, you can observe this by checking variations of your model specification, see what happens if, say, if the coefficient changes so much, if the coefficient estimate changes so much, or if the standard error estimates change drastically, then that's a red flag, right? That you may have to carefully construct your empirical model to address these potential issues of omitted variable bias, the first one, and inclusion of irrelevant variables, right, which increases the noise of your model. Now, the second part of the video, we'll just have to replicate this, at least for the base model. Let's try to replicate this for the base model using R. Right, so this is how we do it in R, right? So we first specify the correlation matrix as we have done in Stata, right? Let's change it to our values, the values that we used earlier. So let's run this. So you have matrix A. Let's try to check. So, okay, this is x1, this is x2. The correlation is assumed to be at 0.6. Right? Now, let's try to, before anything else, let's load the library first. Right? Because this will allow us to generate this vector of randomly drawn set of regressors. Right? So you have MB norm, MVR norm. So this is the equivalent of draw norm in Stata, which basically allows you to generate random variables accounting for the correlation between these two variables, x1 and x2. So let's run this, and you now have a vector. So let's look at the environment. So you have a matrix, basically you have a matrix here, and let's extract those individual variables, x1 and x2. So you have two vectors, x1 and x2. Okay. So let's try to get the base model first, right? So let's assume that you have this data generating process, right? Let's assume that the constant is supposed to be at 20. The beta 1 is 1.9, as I've established earlier, and let's use 0.5 as the coefficient of beta 2. And let's assume that sigma is equal to 1, right? So standardized, standard distribution, standard normal distribution, right? So basically, we're constructing a function, M1, which we will run later on. So this is similar to the program environment in Stata earlier. But in R, we're calling for a function. So M1 is a function. We're defining M1 as a function that we will replicate 2,000 times in line 29. Okay, so let's try to run this. Right? Okay, so Y is your data generating process. You have beta naught specified at 20. You have beta 1 specified at 1.9, beta 2 specified at 0.5 with an error term of mean 0, sample size of nrep, mean of 0, and standard deviation of 1. So standard normal distribution for the error term. So let's run this. And after we construct the function, let's run the simulations. Oops, there's an error. Let me correct that. Okay. Let's see where the problem is coming from. Let's try to run 200 simulations. Oops. Okay, let me just correct that. We have a function, and then we want to replicate that function. So let me try to run this first. Okay. Well, let's try to run this. Oh, there's still an error. Okay, let's correct this. Variable lengths differ. Well, let's try to set it at 1000. Okay, let's try to run M1. All right, so that works, right? So number of observations must be identical. Okay, so let's replicate that 2,000 times. Okay, and then we'll get the sims, right? So you have 3 rows. Maybe we can check this. You have 3 rows, one for x1, one for x2, and you have your column, right? You have your columns basically for each iteration. So you have 2,000. We did 2,000 iterations. Okay, maybe we can get the mean of sims row 2, 1 to 2,000. We can do this. Okay, so that gives us the average, right? Average for x1. So this is the average expected value of the estimate for x1. So for the base model, this is close, right? This is close to the true parameter value of 1.9. Let's do the same for x2, variable 2. So it's in row 3, and we need to get the columns from 1 to 200. So let's try to get the sum. And it's right smack in the middle of 0.5, right? With some variation, 6767. Okay, so that's your base model. So it means that it's correct, right? It's correct. So after 2,000 iterations, the expected value of those estimates is close to the true parameter value of 1.9 and zero point 0.5. Now, what if we encounter this problem? As you have mentioned, let's redefine another function with this. What if we omit x2? What if we omit x2? So when we omit x2, we'll remove this. Oh, sorry, this is the true population value, but we remove x2 from the regression. And let's define this as model 2. And then run the simulations. And let's try to get the average of x1. So let's see what happens. Well, it's still, let's see, what's sim2. Oh, okay. All right. Sorry. Let's change that. Let me change that. This is supposed to be M2, right? Right. So you see, the bias is still the same. The coefficient is still the same as we did in that, like we did in Stata, and it's way off. It's way off the true population value of 1.9. It's 2.19 when it's supposed to be 1.9, and this happened because we excluded a relevant variable from the regression, which is in line 42. We just regressed y on x1, and when in fact you should regress y on both x1 and x2. If x1 is not correlated with x2, this wouldn't be a problem. You can check the first step. You can tweak this code. It's not going to be a problem. But because x2 is a relevant variable for the data generating process of y1, or y1's data generating process, it becomes way off. So the estimates become way off the true parameter value, which is 1.9. Now, what if we include x2 as an irrelevant variable? Right. So yeah, so let's tweak this model, let's tweak this program, and let's write it as M3. This time we'll revise the data generating process. Let's write this model M3, right? Now the data generating process doesn't include X2 anymore. And of course, B2 doesn't really appear anymore. But suppose we chose to include X2 in the regression. So to do that, let's extract the standard errors. And just compare. Right? Right? Maybe we can do the same. So let's run this, and let's run this simulation. And this will be the standard errors, right? Standard error estimates for x1 and x2, right? Let's get the mean. The standard errors. So it's at point 3. 0.04. 0.04. Okay. But what if we, so take note of that, that's 0.04. But what if we exclude x1? What's going to be the standard error? Let's run this again. Well, it's a little smaller. So the base model's standard errors is a little smaller. It's 0.03, right? So that's the correct model specification. Now, when you added x2 in the picture, x2 in the picture, the standard errors will increase from 0.03 to 0.04, right? 2.04, which means that adding irrelevant variables in the model, will increase the standard error, will increase the noise of your regression equation, increase the noise of your regression model. So that concludes our video for today. Thank you so much for watching this. In the next video, we're going to deal with uh, other specification issues, right? And we're going to introduce some other exercises related to OLS.